Okay, the first and actually the easiest of the transformations that you do to a functions graph is to shift a graph. If you have a generic function, y equals f of x, and it could be any of our 5 stock functions here, or it could be some other random function. You can shift it this way. If you want to shift the graph up by c units, the transformation looks like this. It looks like y equals f of x and then a plus number outside the function's main formula. F of x plus a c. If you want to move the function down on the graph by c units, then the transformation is to take the basic function's formula or graph and do minus c to the graph. So vertical shifting is pretty intuitive. Up means plus a value, down means minus a value. Okay, so let me jump to the bottom of the page and show you an example of vertical shifting with this first example. You're asked to sketch the following transformations accurately using the transformations that's detailed right here. So first thing to make note of is that we're referring to the cubing functions graph, which is this one right here. So what you want to do is, since we're starting with that stock functions graph from the cubing function, you want to maybe do a little dotted or like a very faintly drawn version of this graph right here. So the original graph that we're transforming is x cubed. You see that from the formula there. The minus 4 is going to tell us to, since it's x cubed minus 4, we're going to shift it down by 4 units. So what I usually do is I'll just take the original function's graph and do a lightly drawn version of the original untransformed function first. So starting at the origin, for the cubing function, you can go 1 click right and 1 click up, 2 clicks right, 2 clicks right, and 8 clicks up, 1 click left and 1 click down, 2 clicks left and 8 clicks down. So that means the original untransformed graph looks something like this. And notice I'm doing dotted lines here because this is not my final answer. This is just, using this as a reference to produce this new graph. So what it means to use transformations is just to take your knowledge of the existing function that you're analyzing and apply that transformation to its graph to make the new function's graph. So since minus 4 means to take the entire graph of f and move it down by 4 units, take the points that you have here plotted and just move them down 4 clicks one at a time. Okay, so this point, actually, if I try to go down 4, it'll be off the grid, but I can try to approximate it. Be probably about right there. This point at -1, -1 is now going to move 1, 2, 3, 4. Wait, 1, 2, 3, 4 clicks down to right there. The origin point goes down 1, 2, 3, 4 points. This point that used to be at 1, 1 is now going to be 1, 2, 3, 4 points lower. And this point here that used to be x equals 2, y equals 8 will go down by 1, 2, 3, 4 points. So notice, you still produce the same kind of points as on the original stock function graph. See, from here to there in the middle, and then to this, produces the same kind of points you see right there. It's just been transformed based on the fact that you're moving it down 4 units. So the official graph should look something like this whenever you connect the transformed points. So see, I'm just using my knowledge of what the cubing function looks like to produce this new functions graph from the old one. So, in producing the answers like this in your homework, you probably want to do this original dotted version in pencil so you can erase it and then make your final graph in ink. Or I've even seen students do the original graph in one color and use a different color for the final graph. But that's essentially what it means to shift this function down by 4 units, because that's what our shift indicated for us to do. So if it had been y equals x cubed plus 2, I would have taken the original dotted graph of the cube function and gone up 2 units to transform it. Okay, now shifting it horizontally left and right, you got to be careful. See, with vertical, plus does mean up, minus means down. So that's with your intuition. Now with horizontal shifting, you got to be careful. The transformation is actually going to be inside the function inside the function's operation, maybe inside some grouping symbol or inside the square root symbol or inside the absolute value bars. It'll be inside the calculation, kind of like this. So in this case, it has to be inside the cube if I'm dealing with a function x cubed. And the way the transformations work, if you want to move a function to the right by c units, the transformation needs to be whatever the function's operation is with x minus c on the inside of the operation. If you want to move left by c units, the transformation is detailed by y equals f of x plus c inside the function's operation. So, since I do have a grouping symbol here and the operation is right there on the outside, x minus 4 is inside the operation of this function. So x minus 4 means I want to take, I'm using a value of c equals 4. That means I'll take the cubing function and move it right by 4 units. So whenever you're prompted to do these accurately, it means try to refer to the original cubing function's graph and then shift and transform based on that. So I'm going to do the same thing I did right here. I'm going to use those initial 5 points that are on the original cubing function's graph. So again, this is the untransformed version of the cubing graph. And I'm dotting that in just because I'm using it as a reference. And I want to move this right by 4 units. Okay, so you got to be careful. Whenever shifting horizontally, it's easy to get confused and say that right means plus and left means minus. Nope. If it's inside the function, inside the operation, it's always the opposite of your intuition. If it's outside the function, like this minus 4 here, that does mean minus vertically down by 4. But here, minus 4 means right by 4 units. So if I take all these 5 points and move them right by 4 units, this one goes 1, 2, 3, 4 clicks right. This one, 1, 2, 3, 4 clicks right. The origin point moves to here. This point moves to here. And this point moves to here. So I still see the same 5 points. They're just in a different location on the grid because I'm applying a transformation to the graph. So this particular function should look something like this after you've applied the transformation to it. So you see, knowing transformations, knowing how these transformations generate these new graphs from the stock graphs that you're referring to is a very powerful graphing tool that you need to develop as a pre-calculus student, because we didn't have to plot any points here. We didn't even have to use our calculators. If you get to the point where you can generate these graphs without the need for your calculator or plotting points, then you have mastered what these transformations are trying to teach you. Okay. The next transformations I want to show you are some combinations of shifts. Okay. So the first one we're graphing here is a transformation involving the absolute value function. So let me do its original graph. That was a positive 1 slope going to the right, and then a negative 1 slope going at a, essentially a 45-degree angle up to the left like this. So there's the original unchanged absolute value function, and I know I'm dealing with the absolute value function because I see the absolute value bars there, and that's what its original image looks like before you transform it. So the two transformations that are detailed here, you've got a minus 5 on the outside, so that's going to mean down 5. And then you have a plus 3 on the inside of the function's operation, so be careful. Minus 5 on the outside does mean down, but then plus 3 on the inside of the function's operation means left. So that means you're going to want to go left 3 units. So now these can be done in either order. You can do down first then left, or you can do left first then down, because it will still take you to the same point. So what you might want to do is start with the origin point. If you go down 1, 2, 3, 4, 5, and then left 1, 2, 3, this is where the new origin point is going to be. Now here's the cool thing. That's the only transformations we're doing to this graph. So you can kind of think of this as playing the role of a new origin point. We're not doing any other kind of transformation or reflection to the graph. So if this is the same role as this origin point, then I should be able to say I have a positive 1 slope going this way. So notice I'm just slicing all the squares in half on my graph paper, making a perfect 45-degree angle. And then I have a negative 1 slope going this way. So see, knowing the behavior of the absolute value function or any of these functions really comes in handy. Positive 1 slope, negative 1 slope, and that's the only point I had to plot, was based on knowing that origin point got shifted down 5 and left 3 to become this new shifted origin point. And every other point on the graph would have to get shifted the same way. So for instance, if I pick this point right here on the original graph, if I go down 5, 1, 2, 3, 4, 5, and left 1, 2, 3, it's guaranteed to be a corresponding point on the new graph. So it's a very powerful graphing tool that you need to be able to develop, is understanding how these transformations can speak to you and show you how to make a new graph from an old one. Okay, so try this one out. Here's the stock square root function graph. 2 transformations are prompted here, so go ahead and pause the video if you'd like and see if you can do the transformation, and then hit play and compare your answer with mine. So the original graph initiates at the origin, and then you go 1 right and 1 up, 4 right and 2 up, and then if you got room for it, 9 right and 3 up. I don't really have room on this one, but that's roughly where the original graph goes. It looks something like this, sideways half parabola. And the 2 transformations that are done to it are up 2 and under the plus inside the operation. So a plus inside means left. So left 2. So just to make sure you're aware, I mean, here I did vertical then horizontal. I'll do horizontal then vertical because they both take you to the same place. If you take your origin point and go left 2 clicks and then go up 2 clicks, there you go. Next point, left 2 clicks, up 2 clicks, left 2 clicks, up 2 clicks, and then this point, left 2 does put you back on the grid, and then up 2 puts you right there. So keep in mind the origin point is a starting point, so you don't go anywhere left of this. It starts right there and then leaps up and connects to these others in a sideways half parabola shape. It looks something just like that. Okay, so coming up next, we have some other transformations to discuss that involve reflecting your graphs.